Okay, so I just wanted to go through activity 1C1 and 1C2. I'm going to apologize in advance if the volume is up and down. I cannot find my AirPods anywhere, so the mic, I don't even know where it's at on this iPad, so I apologize. But okay, so we did go through part 1 in class, so if you don't have this and if you're struggling with this part, please let me know, because we did go through this in class. I'll quickly go through and say, so number 1 should be closed. Even integers are defined as, like, let's say 2k, or 2 times any integer. So you could always try to do the proof, like 2m, where m is some integer, times 2n, where n is some integer. That would equal 4 times mn. You can factor out a 2 from this, end up with 2 times 2mn, where 2mn is some integer. So whenever you multiply 2 even integers together, you get an even integer, 2 times some integer. So that would be the proof for, that's a very, very rough proof, but that would be the proof to prove that that one is closed. Number 2 is not closed because, like, let's say if we took the average of 2 and 4, right, that would be 2 plus 4 divided by 2, which is 6 divided by 2, and you'd get 3, which is not a positive even integer. But 2 and 4 are, right? So if something is not closed, then you just need one counterexample and call it a day. If something is closed, like this one, you have to prove it using a generalized explanation like this. So 2 times any integer times 2 times any integer. That's 2 even integers multiplied together, etc. Okay. C, all odd integers. Not closed. 3 plus 5 is 8. 8 is not an odd integer. Okay, so this is the kind of stuff that I really wanted you guys to work through in your groups. So I'll quickly do number 4, all odd integers. This one is closed under multiplication. The reason why is if you think of an odd integer, let's say, because it's any, like, 2 times an integer plus 1 would be your odd integers. So let's say if we had like 2m plus 1, where m is some integer, and 2n plus 1, where n is some integer, and you multiply that together, you're going to get 4mn plus 2m plus 2n plus 1. And this I'm just distributing, that's all. So I'm just multiplying them together. So if you were to try to factor this out, I like this plus 1 out here, right? Because the definition of an odd integer is 2k plus 1. So I'm going to leave that 2 plus 1. Or I'm sorry, I'm going to leave that plus 1. But each of these terms have a 2 as a common factor. So I'm going to factor out a 2. And that leaves me with 2mn plus, I'm going to run out of room. 2mn plus m plus n. And integers are closed under multiplication and under addition, right? So this is multiplication and addition of integers, and we know that will result in another integer because integers are closed under multiplication and addition. If you add 2 integers together, you're going to get an integer. If you multiply integers together, you will get an integer as your answer. So that's what it means by closed. So this means that I get 2 times some integer, right, plus 1, well, that right there, that is the definition of an odd integer. So it's closed. So I multiplied an odd integer times an odd integer, and I get an odd integer. So that's why it's closed. Okay? So these, you can continue to try to prove these different ones here. So numbers 5, 6, and 7 have to do with prime and composite numbers, or integers. This one's all prime natural numbers. So you would want to know what that is. So, like, for example, prime, we have 1, 2, 3, 5, 7, 11, 13, and so on, right? So you want to see, is that set closed under addition? If you add any of those two together, do you get another prime natural number? If you do, then it's closed. If not, then it's not closed, right? So if it's not closed, you just have to find one that doesn't work, and bam, it's not closed. Same thing here, all composite, that just means not prime. So that's if you add composite integers together, do you get a composite integer? If yes, it is closed. If no, it is not closed. So you want to try to think of if there's a counterexample or not. And then same idea for G. So all composite integers or the not prime integers and so on. Okay. All right, so let's go and look at part 2. G is actually interesting, or I mean number 7. So maybe, yeah, this one's kind of long. I want to kind of walk through this one. I was just looking at the proof. So number 5 ends up not being closed. So if you like add 3 plus 5, you get 8. 8 is not a prime number. That one's not closed. Number 6 is also not closed. So if I add 2 composite integers, so like 4 is a composite integer, and trying to think here. So if I add, oh my gosh, my brain, 9, okay? 9 is a composite integer. These each have factors other than 1 in themselves, right? 4 has 2, 9 has 3. This equals 13, and 13 is prime, not composite. So this one's also not closed. I'm just going to write NC, NC, not closed, not closed. But 7 actually does end up being closed. So whenever we multiply composite integers under multiplication, you want to think composite integers means it has factors other than itself and 1. And if we multiply 2 integers together, we're just giving them more factors, basically, right? So how the book kind of sets this up, they define like x, like let x equal a times m, where a and m are both some integer, right? And then so I'll say and y equals, and y equals b times n, where those are both some integers, right? So if we want to see if they're closed under multiplication, we want to see, okay, well, x times y would be the same as am times bn. Okay, and these are all just some integer, right? So, I mean, we could rewrite this as a times m times b times n, which these are just 2 integers multiplied together. So all this is doing is giving me more factors. So a, m, b, and n are all factors of whatever the product x times y is. So that means that our answer here is not prime, right? If those are all 4 distinct factors. So right there, it is closed. If you multiply composite integers by each other, you are going to get a composite integer as your answer, because you can't go backwards in the number of factors if you're multiplying, right? So that's a good one to think about. I really do like that one. That's a good one. Okay, so now part 2 is where it starts to get a little bit more difficult. So we have the set H as all numbers of the form 3n plus 1 for n is a natural number under multiplication. Okay, so if we just kind of start playing around with this, I'll let's look at 3n plus 1 times 3m plus 1. Okay, and these are 2 numbers in the set H. I'm just using m instead of n to show a different integer there. So if we multiply those 2 together, right, I'm just going to use distributive properties. So 3n times 9mn plus a 3n plus 3m plus 1. So if we factor out a 3, so I like the plus 1 part, right, because we do have a plus 1. So we need 3 times some natural number, right? So we can factor out 3 here, and then we'll have 3mn plus n plus m, and then this plus 1 is still there on the outside. Right, so I used a term called grouping. I just focused on those 3 terms, and I factored out a 3 from those, and then I still have the plus 1 on the end. So now looking at this, integers are closed under addition and multiplication. So this is really just 3 times some integer, right? So I could say like 3 times some integer plus 1. And that is basically our original definition, right? The natural numbers are within the integers. So really you just have to make sure that they're only the positive integers, right? But your natural numbers are your counting numbers per se. So multiplying them together, you would still get an integer. It would be a positive integer. Right, so this shows that it is closed under multiplication. We get some other 3 times some number plus 1. So that one is closed. Now number 9, all numbers of the form 3n plus 2 for n is a natural number under multiplication. Okay, so the way that we want to think about this is if we were to pick like any 2 numbers, right? So for example, I'll go ahead and pick 8, okay? So 8 can be rewritten as 3 times something plus 2, just like the number 2 can be rewritten as 3 times something plus 2, right? So really it'll be multiples of 2 plus some multiple of 3, if there is one, right? So here, this would be 2, and this one would have to be 0, okay? So now what this is saying is if I multiply 8 times 2, right, that's 16. Can I rewrite 16 as 3 times something plus 2? So the way that you guys can test that is if you just threw an x in here instead and solve for x. So this would be 14 equals 3x divided by 3. So we get 12 and 1/3, or 2/3, sorry. 2/3. Oh my gosh, my brain. 4 and 2/3. I was thinking 12. 4 and 2/3. And that's not a natural number, right? And we don't get something that can be rewritten in this form 3n plus 2. So this one is not closed. That would be a good counter example. And I challenge you to try to find another counter example that you could think of this as well. Okay. So number 10, perfect squares of integers under addition. So if we guys just start writing out perfect squares, so like for example, if I took like 1 squared plus 2 squared, that is equal to 1 plus 4. Is 5 a perfect square? It's not, right? So this was 1 plus 4, right? Or I already wrote that there. 1 and 4 are perfect squares because if you take the square root of them, you get an integer, right? So, I mean, you guys could even do like, let's do, so like 16 plus 25, we get 41. 16 is a perfect square because the square root of 16 is 4. Square root of 25 is 5, but the square root of 41 is definitely not a perfect square. It's a decimal, right? So these are not closed either. That's for up there. Okay, so that either one of those would be good counterexamples. Okay, so the perfect squares of integers under multiplication. So if we kind of just start playing around like 1 times 4, you're going to still get 4. That's a perfect square still. Let's do like a bigger one, like 5. Oh, no, 5's not a perfect square. 25 times 4, right? Those are both perfect squares. That equals 100. That is also a perfect square. So if you keep doing this, you're going to realize, oh, wow, I keep getting perfect squares. So here, how I might approach that is to define like let's let x equal m squared, and I don't need to write let again. And these are very informal things I'm writing here. I'm just trying to give you an idea of ways you can write it. So then x times y is equal to m squared times n squared. And you can rewrite this as mn squared, mn quantity squared. And this is why it's so important for you guys to know all your prereq skills, like being able to rearrange terms, the associative property, commutative property, etc., distributive property, right? Different things like that we want to make sure that we're masters of, because now look at this. This gives me x times y is a perfect square, right? If you square a number, that will give you that perfect square. So it is closed under multiplication. If you multiply 2 perfect squares together, you will get a perfect square as your answer. All right, so set M, all numbers of the form 2 to the n power, for n is a natural number. Okay, so this is number 12. So we want to start thinking, okay, so let's just start small, right? So 2 to the first power plus 2 squared is equal to 2 plus 4, which is 6. Can 6 be rewritten in the form 2 to the n power? Can't, right? So 2 to the n power, let's talk about this. 2 to the n power. Let's let n be here, and this is 2 to the n, okay? So if my n is 1, 2 to the n is 2. 2 to the first power is 2. If my n is 2, 2 squared is 4. If my n is 3, 2 cubed is 8. If my n is 4, 2 to the fourth power, 2 times 2 is 4, times 2 times 2 is 16. Right? So none of those equals 6. We've already passed up 6. So this right away, I mean, the smallest example doesn't even work. So this is not closed. Oops. Okay. And these can be a little difficult, but if you guys use like a table or something to set it up, that might help you visualize it a little bit better. So number 13, set n equals is all numbers of the form 2 to the n for n is a natural number under multiplication this time. So the other one was addition. So now let's give multiplication a shot. So if I just do like 2 to the first times 2 squared, that is equal to 2 times 4, which is 8. But if you remember your exponent rules, if you're multiplying two numbers that each have an exponent and they have the same base, here our base is 2, right? This is 2 cubed. If you do 2 to the 4th times 2 to the 10th, per se, they have the same base of 2. You add the exponents together, that's 2 to the 14th, right? Because if you were to expand that, this is 2 times 2 times 2, which is 2 to the third power, right? So that's why we can just add the exponents. This is definitely closed under multiplication, okay? And you could do it in an arbitrary way, like instead of using numbers, you can do 2 to the x times 2 to the y is equal to 2 to the x plus y. And that right there, bam, that's some form of 2 to the n power. It's closed, right? Sounds good.